Okay, we're gonna give this a try. Filming this video because I am not feeling very good. So we're adjusting the schedule a little bit. You're gonna watch this video. You are watching this video Thursday, and then we'll do AP Problem Friday. But yeah, this is our lesson 5, which features our last integration technique of Unit 7A. We're gonna look at partial fraction decomposition here. So let's get started. We see some algebra developing on the slide here. Starting on the left, we see two rational expressions with different denominators. Uh, we want to subtract one from the other. To do that, we need a common denominator. We see all that work here, just like you would see in an algebra class. And eventually, we have a simplified result over on the right side. Okay. We're very interested in this process because if you look at where we started and where we end up, it just so happens uh, one of those forms is easy to integrate, one is harder to integrate. We actually prefer the version on the left side for integration. The version over here on the right, which is an answer your algebra teacher might have wanted from you that was considered simplified, is actually a lot more challenging to integrate. So, what we need to do is go the other way with this manipulation. We want to take something on the right side and break it down into smaller, simpler fractional terms. We call the process partial fraction decomposition. So that's what we're going to look at today. How do we break the right side down back into the left for the sake of integration? All right, on to the next page. Criteria. As with all of our strategies in this chapter, it's important to be thinking about when you would use it as opposed to something else. Here's the criteria for the partial fraction decomposition. You're looking to integrate something that has a fractional form. Both the numerator and denominator are polynomial in nature. For our strategy to work, we need the degree of the numerator, I'm calling it P here. We need the numerator degree to be strictly less than the degree of the denominator that I'm calling Q. Okay. We would also need the denominator to be factorable into linear factors, meaning x to the first plus or minus a constant. If we meet those conditions, then we know our original fractional integrand can be written as a sum of rational functions. Uh, for each distinct linear factor, the decomposition is going to have a term with that particular factor in the denominator. Okay. Part B, don't worry about this right now. We'll save this for Monday to talk about sort of special case, but you can kind of see what's developing here. If we had repeated linear factors, there's a slightly different pattern, but we'll save that for another day. All right, let's check out example 1. Here we see the integral in play. Okay. Degree is bigger on the bottom, which is what we want. The bottom is also factorable. So in this current form, there's not a lot we can do, but we are going to be able to decompose this thing. So the first thing I'm going to do, I'm going to rewrite the integrand factored out in the denominator. Because of the kind of pre-work we saw on the last couple panels, we know that this particular expression can be broken down into something, I'll call it A, over one of my factors, x plus 1, plus some other value over x plus 2, which was the other factor of the denominator. So we're going to break this thing apart. I just don't know yet what the numerators are going to look like. Okay. Now, I've written out the template of what we want this thing to become. I'm going to play with it a little bit more. imagine that you were sitting right here at this step and you wanted to combine these two fractions by getting a common denominator. If that's what you were doing, you would multiply this first fraction by x plus 2, top and bottom. So a gets multiplied by x plus 2. Meanwhile, the second fraction gets multiplied by x plus 1, top and bottom. So the b specifically gets multiplied by x plus 1. Um, when we write it all back together as a single fraction, we'd have our common denominator, as you can see here. And then you would have a with the multiplier, b with the multiplier, that are really the opposite terms denominators. Okay. Now, as you watch this video, you might be wondering, well, why are we even putting these together? I thought the whole point was to separate these terms into smaller bits. And you're right, that is the point. But I'm writing out this version of the fraction because now I have two different versions of the combined fraction, and we can take the numerators and set them equal to each other. This negative x plus 1 that I'm seeing in the top, some way, shape, or form must be equal to our mystery a value times x plus 2 plus our mystery b times x plus 1. So at this point, I kind of ignore the denominators, and I'm just setting these numerators equal to each other. And the thing you have to keep in mind, this equation that I've got cooking here has to be true for all values of x. All right, it's kind of an identity in that way. And therefore, if I want to solve for a or b, I can plug in useful x values as long as I plug in the same x value everywhere. I can do it. And the most useful x values are the ones that would zero out one or the other of these products. For example, if we plug in a negative 2 everywhere that we see an x, well, the left side turns into 3. On the right side, this a product temporarily disappears, right? Because negative 2 plus 2 goes to 0. And that allows us to solve for b. Negative 2 plus 1, I got negative b over here on the right side is equal to 3. And all of a sudden, I realize b must be negative 3. Great, we're halfway there. Go back up to this identity, and this time let's try x equals negative 1. Plugging in negative 1s will have the effect of disappearing the b term temporarily and allows us to solve for a. Excuse me. The left side becomes a 2 when x is negative 1. The right side is just a, and we're done. So now that I've found this mystery a and b values to complete these numerators, I can update my entire integral. I'm going to take the same template from above. I'm going to use an actual 2 for a, negative 3 for b. And this is just a much nicer thing for us to integrate. The x plus 1, 1x plus 1, 1x plus 2 behave just like x as far as antiderivatives are concerned. So I can just do my basic 1 over x antiderivative. Although I've got a 2 multiplier, I've got x plus 1. The next term is negative 3 log absolute value of x plus 2. Don't forget a plus c. Technically, you could stop right here at this step, but I will tell you right now, there's things we will see later on in this course involving logs where it's definitely in your best interest to condense your logs. So for that reason, I'm going to try and push on you the habit of doing it now. Also, if this were a multiple choice question, there's very good possibility your answer looks like this final line. So, yeah, I've brought my multipliers up as exponents, and then a minus between logs, we can condense, it becomes a division. So here is the simplified answer. All right, one down. I'll do a few more. There is actually a shortcut for your decomposition. Because let's face it, this was a lot of work up here. It's not hard work, but you know, it takes time to get through it. If you like, you can sometimes use a cover-up method. It doesn't work for every example in these notes. If you look ahead, the ones that where you can't use it are marked. But the cover-up method is as follows. You see my thought process in blue off to the right. But I'm taking the original form of my integrand along with its factored denominator. I'm setting it equal to the template that we are using to guide our rewrite. Here's how it works. If I want to figure out what A is, I'm going to look at its denominator. I'm going to identify the x value that would zero out the denominator. In this case, it's a -1. I'm going to bring that -1 over to the left side. But as I'm doing that, I'm going to ignore or cover up the denominator from the A term, but I'm doing it on the left side. So I'm going to temporarily ignore the x plus 1. Here, it literally covered with my hand here. Everything else, I'm going to plug in the x value that we landed on of -1, and the result will be your numerator. If I plug a -1 right here, a -1 right here, I ignore the x plus 1. Here's the work for all that. It's going to land you right at the 2, which is a little bit quicker. And we could do the same thing for B. I look below B. I see -2 would be a crucial x value here. I'm going to plug in -2 over on the left while I cover up or ignore or remove the x plus 2 factor, and the rest of it simplifies exactly into the numerator you wanted. So it's a little bit quicker. You could do it either way. Whew. All right. Moving ahead, we try to do probably three more of these here. Example two on the next page. Honestly, there's not a lot for me to say here once I've already talked through the work in example one. So I would leave it to you to try this problem on your own and use my work here to guide you through it as best you can. Okay. You can see I'm factoring. That's what this work is over on the top left. I used a factor by grouping method thanks to having a lead coefficient greater than 1. So here's my factored form. So I've got my template of what I think I'll be able to rewrite the integrand as with the A and the B. And then I don't even have a lot of work here. I just used cover up, honestly, in my notes. So give it a try or work it out the long way if you like. But it turns out the A here is 1, the B is -2. Make sure you put those over the correct denominators. The updated fraction or fractions to integrate are over here on the right, followed by some answers. All right. Onwards to example 3. So here we have a differential equation. It still is an integration problem. Unfortunately, we don't quite meet the conditions for our technique. We need the degree in the numerator to be less, less than the denominator. So right now it's a no-go, but we can fix that issue with polynomial long division. So here you can see me writing out 3x to the fourth plus 1 divided by x squared minus x. I do like to put in zero coefficient placeholders for any degrees that didn't show up in my original numerator. But then I go through the division process. I'm looking at the highest degree term inside and outside. For example, 3x to the fourth divided by x squared is 3x squared. There's the first term of my quotient. I do my multiplication to the outside, collect my products below. Excuse me. I'm going to subtract. And then I'm going to bring down all these unused terms, collect everything below, repeat the process. Now I've got 3x squared divided by x squared. Actually, no, what does that say? Oh, I'm sorry, I skipped one. 3x cubed divided by x squared gets me to 3x. Multiply that 3x back to the outside, gets me these products here. I subtract, bring down the unused terms. You do go through one more time, where now we do have the 3x squared remainder divided by x squared gets us a 3, which I then multiply to the outside. When you arrive at a remainder whose degree is less than what's on the outside, that's how you know you're done. We're going to take that remainder, put it back over the original denominator. At this point, it does satisfy our requirement for decomposition. Okay. So all this stuff up here is my new integrand. The first three terms are easy. You could just do top 20 rules on those. For the last term, we do need to break it apart with the decomposition. You can see my work for that over here. And then below that, I've got the rest of the problem where I do my separation. I jump to y equals on the left side, integrate everything else, including eventually the decomposition there. Give these problems a try. Please don't just blindly copy my work without thinking through the problems. Make sure that you are able to follow the steps and arrive at the same answers. Okay. Think about one more example is all I can manage for this video. Let's look at example 4 real quick. Again, not too much new here. It's just points out that it is possible to go with our process even when there is more than one, or excuse me, more than two linear factors in a denominator. Oh my gosh, I'm fading here. Sorry. But anyhow, here you've got a denominator that has three linear factors. Difference of squares is happening here. Doesn't really change anything. I set up three terms of the decomposition. I need to find an A, a B, and a C. You could do cover up for each one of those, comparing it back to the original fraction here with the factor denominator. So give that problem a try. Run through the cover up or the longer way if you prefer. Excuse me. But yeah, once you have those numerators, we're going to lock them in up here as we replace the original fraction. Then we're integrating both sides using top 20 rules. And then I did show the condensing again. Okay. Gonna have to cut the video there. We'll do the rest of these examples probably on Monday. Okay. Feel free to email me if you have any questions. Hope to see everybody on Friday. Goodbye.